Section 1.2 is about word problems. And the math parts of the word problems won't be too bad because it'll be like stuff that we've already done. Most of the work is really in the setup. So just getting to the point where you have an equation to solve. When you get to that point, it turns into things that we've already had. But getting to that point, I think that's the challenging part. So I wrote out some steps here that don't necessarily apply every single time, but I think we're pretty close to it. And I mean, like, not every problem is going to have a formula that goes with it and that sort of thing. But what I think you should do, like maybe just as a general strategy, and there's another one in the book too that's, I guess, slightly different from mine, but it's basically the same idea. First of all, and I'm certainly guilty of this one, make sure you read the whole thing before you do anything. Like, rather than like trying to go sentence by sentence and piecing it together like the first time, which I kind of like to just go right away. And that's gotten me into trouble before. So like the first one, I actually have to make sure I adhere to that one too. The second step here, figure out what type of problem you have. That's helpful, especially if it's not this. So the direct translation ones, you can actually see number 1 here. That's what that is, where basically you have a sentence that you just have to turn into something that's represented symbolically, where basically you would turn it into an equation. So that's what direct translation is. It's you have some wording that you then turn into an equation. If you don't have that, you can have a bunch of other things. This section really just focuses on these 3. So direct translation, but then mixtures and uniform motion. The uniform motion ones are going to be relatively easy to catch in this section because they're things that have to do with speed. Right? It'll say something about speed or distance, right? Like those sorts of things are going to be in there. Like something with speed, distance, or time, right? And those are going to kind of all show up in those problems. And then mixtures, you can usually pick up on those pretty easily if these are the only other 2 options, because mixtures are going to be like where you have this much of one thing and then how much of this other thing do you need to, when you mix them together, you get this result. They tend to be phrased like that. Third step, just figure out what things you know already and what you don't know that you might be trying to solve for. You know, if it is a uniform motion problem, if you're thinking like, okay, it looks like we're trying to solve for the distance, but we know how long this took and we know how fast the car was going, or something like that. So just figuring out what you know and what you don't know yet that you're trying to solve for, that's an important step. And if any formula relates the quantities mentioned. So speed equals distance over time, that's a big one. Perimeter, especially of a rectangle, like the perimeter is 2 times the length plus 2 times the width, that ends up being really helpful. Area, like again with a rectangle, area equals length times width, that's a big one. So if any of that stuff is useful, usually one of these words is going to show up in the problem. Either that's the thing you're trying to solve for, or that's one of the given quantities that you already know. So like if you already know what the perimeter is, like if you're given that, that's probably a big red flag of, okay, maybe I should be using the perimeter formula and I'll probably have to solve for length or solve for width or something. Or both, right? It might be, here's the perimeter, this is how the length and the width relate to each other, and then figure out what they are. And that segues right into this next thing. If one unknown quantity can be written in terms of another. That happens with things like perimeter, where sometimes it'll say the length is 3 times the width. So then you could write, instead of just having L and W in your formula, you could replace L with 3 times W. And that's helpful, because the fewer variables you have, the faster you can solve the problem. So that's why in the second sentence, I put that when you assign variables to the unknown quantities, use as few variables as possible. So if you did have that the length is 3 times the width, and you're going to draw out the rectangle and you're going to label everything, instead of using L and W, I would use 3W and W. Because then that'll put you into a formula where then you're probably only going to have one unknown. So then the solving is going to be really fast. Then finally, the math part, when you translate the problem into an equation. And once you've got that, then you just solve the equation like you normally would. Check your answer to make sure it makes sense. So like if you're solving for length and you're getting a negative number, that doesn't make any sense. If you're solving for length and the length that you get is longer than the perimeter, that doesn't make any sense, or something to that effect. So that's, I guess, a thing to look for at the end. But usually checking for these doesn't really end up taking very long, which is nice. But let's see. With the examples that we've got, I think with this particular set of notes, it's the first 4 are direct translation, number 5 and number 6 are mixtures, and then number 7 is uniform motion. So with the first one, this is a direct translation, and some of the key things are just if you can kind of pick out words where you know what they turn into symbolically. So 1 less than 2/3 of a number is 7. So there are 2 that jump out right away, I think. One of them is the word less, because that is subtraction. So less right there, I'm going to say that's subtraction. Then 1 less than 2/3 of a number is 7. The is you could actually replace with an equals, and this would read the exact same way. But symbolically, the equals is the thing that you actually draw. So I'm just going to put that in too. And I'm going to say the word is going to turn into an equals. So that helps. Then the other thing is 2/3 of a number. So a number, that's unknown right now. So I'm just going to take this phrase, kind of draw a bracket around it. And I'm going to say that is going to be our unknown. So that'll end up being x. And then the of, so 2/3 of x, that would be 2/3 times x. So I hope I have enough space in here to write all this stuff. But the word of, that's going to be multiplication. Okay, good. Fit it all in there. All right, so then here, x is going to be our unknown number. Okay, well then, right from here with the direct translation, if you know what the operations are and where the equal sign is and that kind of thing, you can probably jump right to doing the translation because you don't have multiple unknown quantities. There's only one thing that you don't know, whatever this number is. So there's no rewrite one unknown in terms of the other unknown or anything like that, at least not yet. That will happen later. But we've pretty much got a good handle on this. We know the equal sign goes here, and the 7 is going to go on one side, and the other side should be 1 less than 2/3 x, which I think most people would write that as 2/3 x minus 1. So to translate this into mathematics, that's what you're going to have. You're going to have 2/3 x minus 1 equals 7. Right, the 7 I think is self-explanatory that that's what goes on one side of the equation, but on the other side, to write this, you can't really write this one from left to right. It would be nice if you could. I mean, I guess you could if you did it as -1 plus 2/3 x, but most people don't write it that way. Most people like to have the multiplication part first. So if you're going to do it that way, you'd have 2/3 times x and then minus 1 afterwards to take care of the 1 less back here at the beginning. But you could write it as -1 plus 2/3 x. Eventually you'd end up with the same answer, so it's not like it's wrong. But then once you're here, then basically you're just solving an equation. And I guess there is a fraction there, so if you want to clear fractions first, nothing wrong with that, right? It's only the 1, so you just have to multiply both sides by 3. So we can do that. So 3 times 2/3 x minus 1 would then be equal to 3 times 7. And then we'd have to distribute the 3. So 3 times 2/3 x minus 3 times 1 equals 21, since that's what 3 times 7 is. The 3 times 2/3 x, right? You could view those 3's as canceling or dividing out, and you'd have 2x minus 3 equals 21. And then you're just solving a linear equation now, right? Because then we could add 3 to both sides to get the 2x by itself. And then we'd get that 2x equals 24. And then from there, you divide both sides by 2 to get x by itself. So 2x divided by 2 equals 24 divided by 2. And so then that means that x is going to be 12. And that is the answer. So the actual math part is not that bad, right? So I guess really here, once we got this, the 2/3 x minus 1 equals 7, after that, it turns into stuff that we've done before. But it's getting to this point, right? That's the tough part. So if it's a direct translation problem like this, the thing that I think helps if you don't see what to do right away is kind of what we did here, where we went through this sentence and just kind of pointed out like, okay, this is an equals, this is a subtraction, this is multiplication, that kind of thing. I think that really helps. So sometimes you can see it right away and you go, oh, it's this. And that's fantastic when that happens. But if you don't see it right away, then kind of breaking down whatever sentence you've got and saying, okay, this is the symbol that this would turn into, this is the symbol that that would turn into. I think that would be a good place to start if you can't see what to do right away. Next, with number 2, one number is 3 less than twice another number. So this time we have 2 unknown numbers, and one is written in terms of the other one. But we could start where we started last time and kind of point out what we've got as far as like the words that are showing up. So less than, right? That's going to be subtraction. There. Wasn't letting me get that B in there. And then the twice is actually multiplication, right? Because twice is doubling. So I'm going to say that twice. Not only is that multiplication, but I'm just going to say multiply by 2 to make it a little more specific. And then let's see, what we've got is that the is you could view as an equals here, but it's an equals in terms of like this unknown is equal to this expression involving this other unknown. So that's not actually going to get us to the final equation that we're going to solve. This one is, though, because it's going to be first unknown plus second unknown equals 51. So that is in this second sentence, that's an equals. All right, so what I'm going to do is I'm just going to say we've got 2 unknown numbers that we've got to figure out, right? So I'm just going to say that the first unknown number is x. Right? I got to call it something, right? And we don't know what it is, so just any variable placeholder would work. You want to call it x, you want to call it n, you want to call it a, like you want to call it z, that's fine. And then the second, and this is where we're going to use the first sentence, because one of these can be written in terms of the other. So this is where I'm going to do it. So the second unknown number, so 3 less than twice this first one, unknown. So then that would be twice x, right? So 2x, and then minus 3, because it's 3 less. And then we use the second sentence, right? So since we know that the sum is 51, then what that's going to tell us is that if we add these two together, we got to get 51. And I'm going to put the 2x minus 3 in parentheses just for effect, just so I can point at it and say, there's the second unknown number. But you don't actually need that set of parentheses here. Like mathematically, it doesn't do anything. It's just for, I guess, organization and for effect. So first unknown plus the second one, the 2x minus 3. When you add those together, you've got to get 51, right? So this part right here is essentially the second sentence because we're adding our two unknowns together, right? There's the first and there's the second in parentheses, and we have to get 51 out. But like I said, the parentheses don't actually do anything. So I'm going to get rid of them. I'm just going to say, well, then this is really just x plus 2x minus 3 equals 51. I guess I could combine terms a little on the left, those two x terms, and say 3x minus 3 equals 51. And then get the x term by itself. So if we add 3 to both sides, we're going to end up with 3x equals 54. And then get the x by itself if we divide both sides by 3. So 3x over 3 equals 54 over 3. So then x is 18. Okay? So then that's part of it, right? So what we've got right now is that x equals 18. But if x is 18, that's one unknown. The other one is 2x minus 3. And so then that's going to be 2 times 18 minus 3, which is going to work out to be 33. Because 2 times 18 is 36. You subtract 3, you get 33. So then that means that our solution should be 18 and 33. And I guess as far as like a check is concerned, you could say, well, if you add up 18 and 33, you do indeed get 51 like you're supposed to. And then the other thing is, okay, if you take 18, multiply by 2, and then subtract 3, you get 33, right? Which we just did in the previous step. So looks like we're all set with number 2. Number 3. Anne has taken 3 of 4 tests for her math class, and her scores are 52, 69, 72. What grade does she need on the 4th test to get an average of at least 70? Okay, first of all, as far as values that make sense, 2 of these are really close to 70, and one of them is a lot lower. So if the 4 tests are equally weighted and she's going to get an overall average of 70, that 4th one actually needs to be pretty high, right? To kind of balance out this one down here being really low. So if we were getting like something around 70 or less than 70 for a final answer here, right away we'd know that that's wrong. I would imagine here we're probably going to need, just kind of eyeballing this, something in like the mid to high 80s if I had to guess. So let's see what happens. I guess the first thing is the way that you would compute the average. So if you were just going to compute the test average, I'm going to write this just ignoring what the numbers are for a second. But the test average would be that you would add them up. So I'm just going to use T1, T2, T3, and T4 for the 4 tests. So like T1's the first test and T2's the second and so forth. So there's T4. And then we're going to add all those up and we're going to divide by 4, right? But then we know what T1, T2, and T3 are because they're right here, 52, 69, 72. And we also know the test average needs to be 70. So what I'm going to do then is I'm going to say, well then, we're going to figure out what we need to get the test average to be exactly 70. And then we can say, you know, if anything above that would give her an overall average above 70, right? But let's see, T1 is 52. Then T2 is 69. And T3 is 72. And then T4 is the thing we got to figure out. And then divided by 4. Okay. Let's see. I guess the next thing is we do have this fraction here, which we could deal with that immediately, but I'm actually going to clean up this numerator first. So if I add those 3 numbers together, let's see, 72 and 52 is 124, and 69 should be 193. So this is 193 plus T4 over 4. And then we can clear the fraction or cross multiply if you want to view it that way. That would effectively do the exact same thing. But I'll write it out as clearing a fraction. So 4 times 70 equals 4 times 193 plus T4 over 4. And then those 4s are going to cancel. 70 times 4 is 280. So then 280 is equal to 193 plus T4. And then if we subtract 193 from both sides in order to get T4 by itself, then we are going to get T4 by itself on the right side. On the left, let's see, that is 87. So I had a decent estimate, right? Mid to high 80s. Yeah, that's in there, I think. So that's the answer right there. And I guess, we can go back and check it and make sure it works. So like if you want to go through and do the check, I guess here we do have some space. So let me section this off. So the test average should be then 52 plus 69 plus 72 plus 87 over 4. And let's see, I'm just kind of winging this in my head. So let's see, that'll be, if you add the first two, you get 121. And if you add the second two, you get 159. And let's see, then if you add those, that's 280. And 280 over 4 is 70. So checks out. All right, so that one's set up a little bit differently, but we can still do it, right? And I guess you don't have to use a T4 here. If you just want to keep calling the unknown X, there's nothing wrong with doing that. And I mean, whichever way you want to do it, it looks like what we should get here is 87 for what she would need on the fourth test. Number 4, this one is also a direct translation, but it's a little bit different, I guess. But here we go with the doubled again, right? So just like before, doubled means multiply by 2. And then when the farmer sold 1,250, that right there is where we're going to subtract. So basically what happened to the rabbit population? We can start off with the original population, whatever that is. So I guess and that is the thing we're trying to figure out, right? What's the size of the original rabbit population? So I'm going to say that X is going to be the size of the original rabbit population. And then if we see what happens, which is basically described in the first sentence, where the original population doubles, so it's multiplied by 2, so that would be 2x, right? And then after that happens, the farmer sells 1,250, so subtract 1,250. And then the second sentence, that the number of rabbits remaining is 5,800, that tells us how many we're left with after those things happen. So what we've got right now is that first it doubles, so we have 2x, then he sells 1,250, so we can subtract that off, and then what we're left with at that point is 5,800. So those expressions have to be equal, right? Because basically what it says in that second sentence is after these things happen, then this is where we are at the 5,800. And then this is solvable, right? And it's not too bad, right? You'd add 1,250 to both sides. And then we're going to get that 2x is equal to 7,050. And then to get x by itself, divide both sides by 2. And it looks like what we're going to get is 3525. So X is 3,525. And I suppose to get the units in there, 3,525 rabbits. And there we go. So this one to me felt different, which is why I wanted to include it in here. And I thought it would be nice to have one with a different look. And the work doesn't look that hard, but I think this is one where like it's phrased in a way where you actually do go left to right, but it does have a different kind of feel to it. So, but it is another one where it is a direct translation, where you're taking the stuff in the first two sentences and turning that into an equation. So basically what you end up with is the first sentence is the left side and the second sentence is the right side. It doesn't always work out quite like that, but sometimes it does, and it does here. And I think that would be all the direct translation stuff, because then the next thing is mixtures. So mixtures don't have to be like mixtures of fluids, although a lot of times they are, right? It'll be like you have this drink with this much orange juice and you want to have the drink with more orange juice in it, so how much pure orange juice do you have to add, or things like with acids and stuff. So yeah, sometimes it is actually like literally mixing stuff together. But you can also have finance ones, and that's like what number 5 is. All right, so we have that Arlene invested some money 2 different ways. Savings account yielding 7% annually, and some CDs yielding 10% annually. So if her initial investment was $23,000, and then the annual interest income is $2,030, how much money is invested in savings, how much is invested in CDs? So like, how is it split up? That's what we're trying to figure out. So we actually have 2 unknowns that we're trying to get, right? How much is invested in savings? That's unknown number 1. How much is invested in CDs? That's unknown number 2. But we know what the total investment is. So these 2 unknowns, they got to add up to $23,000. That helps. So we do know that, and I think that's a good starting point. So I'm going to say that the total amount invested is $23,000, right? We know that, and it's broken up into 2 pieces. So I'm just going to draw in some arrows that kind of make 2 pieces here, and we don't know what they are, right? So the first one, I'm just going to call that X. So the amount that's invested in savings. So I'm going to say if X is invested in savings, and I know I'm leaving off the units, I don't have the dollar sign there, but I'm trying to keep it a little less cluttered. I'll stick the dollar sign back in at the end. But if X is invested in savings, remember that plus whatever I put down here has got to add up to $23,000. And this is where I'm going to use it. I'm going to say that how much has to be invested in CDs would have to be this number. It would have to be 23,000 minus X. And that'll be invested in CDs. And it's that the total's got to be 23,000. That's how I can do this. And this is part of using as few variables as you can. Because you could say, X is the amount invested in savings, and then Y is the amount invested in CDs. But then you'd eventually have to replace Y with this in order to be able to solve it. Or you'd have to replace X with 23,000 minus Y. I guess that would also work. But now that we have that set up, then we should be able to figure out the 2 ways that you can write the interest income. Because that's actually how we're going to put this together. And with the mixtures, a thing that's a really common way of handling it is to make a table. So we could do that here, where we could say, if you want to make a table, we could say, okay, we've got savings, and we've got CDs, right? We've got two, and then there's going to be a total down at the bottom. And then if we have the amount invested, we know what those are, because for savings, we're calling that X. For CDs, we were calling that 23,000 minus X. And then the total is 23,000. Right, so we know that. And then, let's see, then the interest rates. So the interest rate for savings, it says 7%. It's better to write that in decimal form. So I'll write it as 7%, but then I'm going to convert that and say that's 0.07. And then for CDs, it's 10%. So then you could write that as 0.10 or 0.1. And I guess another thing is, this is just a problem that we're working through. But honestly, those interest rates are insanely high, right? Like a savings account yielding 7% annually. I mean, you would take that one every day of the week, right? I mean, that's about what you would expect to get out of having like an S&P tracker, just with no risk at all. And then I guess the other part would be the interest income. And this is the key, because this is where we get to equate stuff. Oh, and there is no total here, right? Because it's not like you could somehow combine these together. So there is no total interest rate. There will be a total interest income because it's the 2030 up there. So what you'd have for interest income, generally it's the interest rate multiplied by the amount invested. So for the interest income for savings, you'd have 0.07x. Then for CDs, you'd have 0.1. I guess I might as well just write it as a 0.1. That 0 at the end doesn't help us. Times 23,000 minus x. And then for the total, that's the 2030. But what you have here, like when you add these two individual interest incomes together, you have to get the total, right? Because she's only investing two different ways. So the interest income from the savings plus the interest income from the CDs, that's got to be equal to the total interest income, which we have a value for that. And that is actually how we can get all this to work. So I hope I got enough space down here. But what we're going to do is we're going to have 0.07x plus 0.1 times 23,000 minus x. So when you add those two individual interest incomes together, you've got to get the total, which is the 2030. I guess the first thing is that we could clear fractions. So if we were going to do that, then this decimal is carried out to two places, that 0.07. So you have to multiply both sides by 100. And because I'm almost out of space here, I'm going to skip to the point where you would just have the 100 distributed. So 100 times 0.07x plus 100 times 0.1 times 23,000 minus x equals 100 times 2030. All right, well then this will be 7x. Then 100 times 0.1 is 10, so 10 times 23,000 minus x. And then on the other side, you multiply by 100, that adds two zeros. So 203000, so that's 203,000. Then we can distribute that 10, and we're going to have 7x plus 230,000 minus 10x equals 203,000. And then we're going to have to solve it from there. But this isn't too bad, I guess, except for the fact that there are some giant numbers. So let's see here. I can combine terms a little bit from the 7x and the minus 10x and say that's minus 3x plus 230,000 equals 203,000. And the next step would be that you would subtract 230,000 from both sides. I've got to try to conserve space here a little, and because I wrote that table way too big. But if you subtract 230,000 from both sides, you get that negative 3x is equal to negative 27,000. And then if you divide both sides by negative 3, you would then get that x is equal to 9,000. So that's what x is. And then the other number that you would need is 23,000 minus x. And so then that would be 14,000, right? Since 23 minus 9 is 14. So then what you would get for the answer would be that you'd have 9,000 in savings, and then, oh, my pen got stuck. There we go. 14,000 in CDs. And that looks like it should work. All right, so one thing I do want to point out is that with any kind of mixture question, a lot of times making the table helps if you don't see the whole thing right off the bat. Because once you make the table, then you see a thing where it's like, okay, when you add these two pieces together, you have to get this piece. And that always happens. It's not just that it's happening here with the money. It'll happen in the next one too. With the alcohol solution, you can see it down at the bottom of the screen. The exact same thing is going to happen. So if you don't see what to do right away with a mixture, I think making the table helps. And I guess maybe that's one of those things where it might not be the best thing for everybody, but I think for a lot of people that would be a good next step. Just like, all right, I don't see the whole thing right off the bat, so if I start making the table, then maybe I can piece this together. I think that's a good way to go. But number 6 is another mixture. So how many gallons of an 80% alcohol solution must be mixed with 30 gallons of a 24% solution to obtain a solution that's 70% alcohol? Okay. Well, let's see. The traits that we have are the percentage of alcohol in the solution and how much of it there is, right? Because this one, we know there's 30 gallons. This one, we're trying to figure out, so I guess it has X gallons for now. So, all right, let's see. Well, if we're going to make the table, we'd have the percentage of alcohol. And then we would have, let's see, I guess the amount of solution. So I'll say amount of solution. And then what else could we get out of these? Like, well, if we multiplied them together, we could get the amount of pure alcohol. So that actually might be helpful and actually will be helpful. So let's see, amount of pure alcohol. And then these two amount ones are going to be in gallons, but I'm going to leave the units off for now. So the percentage of alcohol, just going through that first sentence. So that first mixture is 80% alcohol, which as a decimal, we can write that as 0.8. And then the amount of solution, here we don't know, right? It's how much of that do we need? So it's going to be an X. Then the amount of pure alcohol, well, it would be the percentage of alcohol times the amount of the solution. So I guess here that's just 0.8x. But then the next one, where we've got 30 gallons of the 24% solution. So a 24% solution, or 0.24. Then the amount of solution is 30 gallons. And then over here, you'd have 0.24 times 30, which works out to 7.2. Okay. And then we want the total. So I'm just going to put in a line right here. And then what we want to get is a solution that's 70% alcohol, or as a proportion or decimal, 0.7. So how much would you have to have? Well, if you have X gallons of this first solution and 30 of the second, when you mix them together, you would have to have X plus 30. Right? Because you just take one amount and another amount and you pour them into the same container, it would have to be those two amounts added together. That's how much you would have, right? Like that's how that would have to work. And then the amount of pure alcohol, well, we could still multiply across and say this would have to be 0.7 times X plus 30. But then if we multiply that out and distribute that 0.7, you'd have 0.7 times X plus 0.7 times 30, but 0.7 times 30 is 21. And then we should be able to solve it from there, because the amount of pure alcohol when they're mixed together would have to be the amount of pure alcohol in the first solution plus the amount from the second. So again, we end up in that situation like we did with the money, where it's where you have a total amount that would have to be equal to what you get when you add together two individual amounts, right? It's just like with the interest income. It's a totally different context, but you end up with the same kind of thing. And that's not an accident. Mixtures always kind of work out like this. But if we do that, we're going to have 0.8x plus 7.2 equals 0.7x plus 21. Then I guess the first thing would be to cast out those decimals. So they both just go to one place. So we could multiply both sides by 10. And I guess, again, I'll just jump to the point where we've got the tens distributed. So 10 multiplied by every single thing in the previous line. And we end up there, which now these are all going to simplify. So 10 times 0.8 is 8. So we'd have 8x. And then plus 10 times 7.2 is 72. Then 10 times 0.7 is 7. And 10 times 21 is 210. And let's see, then from there, we could subtract 7x from both sides. And I think I can squeeze this in. We're going to have x plus 72 equals 210. And then from there, so I guess I'll just recopy it first. So x plus 72 equals 210. And then to get x by itself, we're going to subtract 72 on both sides. And we're going to get that x is 138. And I suppose then 138 gallons would be the final answer. Okay, so that's a big number. And you think, well, that's a lot bigger than 30. Does that make sense? Actually, yeah. Because we're starting off with 30 gallons of this 24% solution. 24% is way below 70. So to add in enough of this 80% solution to where the total mixture is 70%, you're going to need a lot. You're going to need way more than 30, certainly. So the fact that this number is really big actually does seem pretty reasonable. It seems like that makes sense. And let's see, I think that's it for the mixtures, because then the last one is one about speed. So if it's a question about uniform motion, so like this one, the formula for speed, that speed equals distance over time, you're probably going to use it. And you can use that in sort of like a table form too. But what we've got, so it says that Karen drove at a steady speed for 2 hours on the turnpike. Then she slowed down and traveled 16 miles an hour slower on secondary roads. And then we know how long the entire trip took, and we know how much it covered. So look at what this is. This is total time, and this is total distance. And then we want to figure out what her speed was on the turnpike. Okay, so I like to draw pictures and things if I can. So I guess this one I sort of can. So there's basically two pieces of this journey. There's the turnpike part, and there's the secondary roads part that's going to be longer. Because if the whole trip took 7 hours and she was on the turnpike for 2, this other part's got to be 5. So this is the start, and then down here is the finish. And we know how long the whole thing took. Right, it took 7 hours. So then this part right here would be the turnpike. It says that happens first. So the turnpike, and that's 2 hours. And then after that, we've got secondary roads. So secondary roads, and that's going to be 5 hours. Then, let's see, we could also figure out the speeds here too. Or at least a way to relate them to each other. Because whatever her speed was on the secondary roads, it's 16 miles an hour slower than it was here. So I'm going to say if on the turnpike, if her speed was X, then here on the secondary roads, her speed would have been X minus 16, right? Because it's 16 miles an hour slower. Other stuff that we know, we also know, I guess I'll just put this off to the side, that the total distance is 214 miles. So we're going to need that. But let's see, we've got, I guess it would be the turnpike, then secondary roads, and then the total, and then we've got the speed, and I guess we've got the time, and then down here we've got the distance, right? Since those three quantities all relate to each other, since speed is equal to distance divided by time. So the speed on the turnpike, we said it was X. The secondary roads was X minus 16. Okay, and then I guess I should kind of separate these out. All right, then the time, let's see, this was 2 hours and this was 5 hours. Right, and really we back solved for the 5 because we knew the total was 7, and then we knew it was 2 hours on the turnpike, which forced the time on the secondary roads to be 5 hours. But then the distance, the total distance is 214. But then what would be the distance here? Or, right, for the secondary roads or for the turnpike? The thing that you can use, and I guess I can kind of write it off to the side, is usually when you think of the speed formula, it's like this, where it's speed equals distance over time. But if you multiply both sides of this by time, you would get that speed times time is equal to distance. And that's more helpful for us because that shows us how to get distance. And you go, oh, we can just multiply speed and time together. Okay, well then x times 2, most people would write that as 2x. And then 5 times x minus 16. But then the total distance, the 214 down here, would have to be equal to the distance she traveled on the turnpike plus the distance that she traveled on the secondary roads, right? So look, even when you have this this type of problem where it's about constant speeds, it kind of looks like a mixture, doesn't it? We've got the table. We've got this column where we're saying we got this total that would have to be equal to what you get when you add these other pieces together, right? So this does look kind of familiar, but that's good that they're so similar, right? Like that provides some consistency at least. But then it is true that you would have to get 214 when you added 2x and 5 times the quantity x minus 16. So that should be equal to 214. I'm going to distribute that 5. So we have 2x plus 5 times x minus 5 times 16, which is 80. That's equal to 214. And we can combine terms a little and say that's a 7x minus 80 equals 214. And then we're going to add 80 to both sides to get the 7x by itself. So then it looks like what we would get is that we would have that 7x is equal to 294. And then if you divide both sides by 7, 294 divided by 7 is actually an integer. It works out to be 42. So x is 42 miles per hour. And that's what we were asked about, right? The speed on the turnpike, we said that was x. And it looks like we've got it, right? So if you wanted to figure, or to do the check here, I think I've got enough space to kind of box this in. Right, so this right here would be the answer. The x equals 42 miles per hour, since that's the turnpike speed. But in order to do a check, so the turnpike speed is 42. So, and we can check just to see if the distances work out. Right, so 42 times 2, right, 'cause it's 2 hours on the turnpike. And then if it's 42 on the turnpike, 42 minus 16 is 26. So 26 would be the speed on the secondary roads times 5. So that's equal to 84 plus, and that's 130. And if you add those together, you get 214, which is the total distance. So looks like we got the right number, right? Looks like that 42 is correct.